Okay, in this presentation we are going to look at mathematical operations and mathematical functions in Julia. We're using Julia version 1.6.1 and we are using Jupyter notebooks. So essentially what I'm going to look at is powers like 2 to the power of 2 and so on, exponential functions, logarithms, roots, and a couple of other things along the way. Okay, so just actually before we get into some functions, let's just see how we would calculate the power of a number there. So we have 2.0 to the power of 2, and it should come out as 4.0. If we want the square root of 9, or we want to sort of express a number that is a root, I think a handy way of doing it is just actually use the chevron operator there, which is to the power of, and then just specify the power in brackets. Okay, so that's the square root function there. Let's have a look at that. Okay, and if that actually applies to getting the inverse of numbers, so just as a quick remark, what we might do is set up this little vector of 5 numbers, 2, 4, and 5, and get the inverse of them, which is to say the power to the -1 of those numbers. So we have a little vector there of 3 numbers. So when we are applying a vector, we have that little dot there, dot chevron to the power of -1. So that should give us a half, a quarter, and 1/5. 1/2, 0.5, 0.25, and 0.2. Okay, so that's the main part. Now let's look at some uh, proper functions here. Okay, so first off, we have the square root. Here we have the square root of 8. Straightforward enough. Let's just try that out to see how that would work for a negative number. Okay, so here we have the square root of 49. That's going to give us an error there. Okay, now we'll come back to that, how we would do that shortly. Okay, so it has to be a positive number. If we want to apply it to a vector there, 1, 4, 9, there we go, square root dot sqrt dot in brackets the vector that we are interested in working with. So just for the sake of comparison, let's look at that there. Okay, that's a point I made already. I just wanted to sort of re-emphasize that. Looking at complex numbers, so essentially what we have to do is just specify it as a complex number. So there we go, 1.41 plus 0.01. So that is mathematically, numerically the same as what we've done, or the square root of 2, but not in terms of types. Let's just look at the example we were working on already. 0 plus 0.0 plus 7.0 IM. So, okay, that's what we would expect. Just as a remark, what is that type? Types are very important in Julia. So it's a complex, okay, type. Okay, so just watch out for that. Types are very important in Julia. If you're used to R and other stuff, like the emphasis is not there as much in R or other programming languages, but you have to be much more, pay much more attention to it in Julia. Okay, so we also have the square root, and this actually will accept negative values. Sorry, the cube root, CBRT. Okay, so the cube root of 8 is 2.0. Uh, cube root cube root of -8 is minus 2.0, and so on. Okay. Uh, Again, that would be equivalent to the power of 1/3. So, you know, that approach there is always useful. Okay. I mean, it's great to have functions like this, but just specifying chevron and the power is also handy. Okay. So applying that to a vector, cube root to a vector, just remember the dot. Okay. Likewise, same here. Okay. And let's apply it to complex numbers. Okay. So we get an error here. That's interesting because we don't get it for um, square root. It worked fine for square root. Anyway, but it's sort of, it's a case of putting a lot of attention to it there, but this does work here. Okay, the power of 1/3. Okay, so you know that's why this approach is always useful to have. Okay, if necessary. This is an interesting one. Hypot, which computes the hypotenuse. Okay, this is like Pythagoras' theorem essentially. A squared plus the square root of a squared plus b squared, or x squared plus y squared. Okay, so this will give us, suppose we have two sides of a right angled triangle, and the two sides that are joining the right angle are 3 and 4. That means our hypotenuse will be 5. Okay, just like Pythagoras' theorem. So you can check that, use that to check Pythagoras' theorem and so on. So it's a handy little one there. Okay, now, does this work? Oh, that doesn't work. Okay, we're supplying a vector. Should it? There we go. Oh, no, that does not work. Okay, the question is, should it work? And the answer is no, that really shouldn't work. This is approach here. Sorry, I'll go up a second here and just show you what I mean. So this approach here will get the square root of 15 on its own. Sorry, the cube root of 15 on its own. Okay, and do that one job. So this is one argument and has this output. Okay, then it will move to the second item and get this output. Okay, so it's the cube root function here is working individually on each item on in the vector. Okay, so that should work, but in this case, that is not what is going on here. We have the first argument and the second argument. They have to be put in together, basically. Okay, so this makes no sense. Okay, to actually try and supply a vector. So because a vector is a list of individual arguments. For hypot, we need two arguments, the two sides of the triangle. Okay, so that should work. Okay, so again, this should not accept a vector. All right, now exponential. This one is straightforward enough. The exponential of x, e to the power of x. So let's look at that. 2.718. Okay, and a vector supplied as an argument, 4-element vector. So that is the exponential of all of those four numbers. Okay. Now, there's some variants of that are quite useful for various reasons in mathematics. So you might see this function pop up quite often. In certain cases, it's a bit of a strange one, an unusual one, until you find a worked example or sort of a domain where you actually will use this a lot and use this function a lot. This is why you have good code vocabulary. So let's just look at that. It is the exponential of exponential minus 1 of 0.15. Okay. And so for x near 0. And let's do it again. Alright. So let's just actually just check what that does. And the exponential of 0.15. Yeah. So it's probably just saves a little bit of typing, that's all. You know. But really what is in the background is just the way it will solve it numerically. Now, just actually, it says it will accurately compute e to the x minus 1. In the background, there is computational algorithms used to calculate these numbers, and sometimes accuracy is important there. So if you were to go do something a little bit differently, you probably would not get the same sort of accuracy. Okay, probably very hard to tell if you're a beginner, but you probably, as you become more familiar with this sort of stuff becomes clearer, and as to the relevance of the accuracy and the different algorithms used to calculate them in the background. Okay, so just make a remark that you know it's there. Okay, this is another one, LDXP or LEXP of x and n. This will compute x times 2 to the n efficiently for integers of n. Okay, so let's try that out. So that is equal to 4 times 2 squared, 2 to the power of 2, and we get 16. Let's try it out for a different one. 3 to the power of 3. 3 times 2 to the power of 3, 24. Now, again, it seems very arcane to use a function like this, but what will happen is that every so often there will be use cases where it is perfect for the situation and you might use it a lot. Okay. Now, logarithms. So, log of x computes the natural log of x. Okay, so we have log of 2.78, or let's just make that 2.718. Okay, we get a value close to 1 because that is actually Euler's constant there, or close enough to it, 2.718. And if we get the log of that, we just get 1. Okay. So that's just essentially demonstrating it's a natural log. I just picked that number there just to emphasize that is the natural log and how to check it yourself. So we have log b of x. So what happens if you specify two arguments? It assumes that the first one is the base. Okay. Now this is different from other programming languages because, for example, in R, usually it assumes that the first argument is x, and the second argument is the base b. Okay, so just watch out for that. Okay, so log of 2 to the base 4 is 0.5. Okay, and log of 4 to the base 2 is 2.0. So just, you might notice that it comes into the order that is opposite to the way I verbalized it. The base is first. Okay, so just watch out for that, particularly if you're used to other programming languages. So I think actually I'm just making a point here about just sort of checking the bases and so on. So essentially I've sort of actually covered this already actually, so I won't go over it again, but essentially just actually, knowing what exactly this command does, what the base is, and how you would specify other bases and so on, because just be careful with the log function in that respect. Now, in addition to log of x, we have a special command. It's defined as log to the base 2. So log 2. There we have log of 8 to the base 2. That should be 3. That's straightforward enough. I think that one's straightforward and simple to understand. Log of 10. Log to the base 10 of x. So there we have 10,000, and that is 10 to the power of 4. Okay. So the log of to the base 10 of 10,000 is 4. Okay, so those are straightforward enough. They're just a way of specifying the base. So finally, again, comes up every so often that you have these special functions for values close of x close to 0, and accuracy is important. Numerical accuracy is important. Here is one, log 1p, log of 1 plus essentially. There we go. The last case will not work because it is the minus 1.01. If you add 1 to that, you still get a negative number. So it does work in this case. Okay. Again, it's a sort of bit of a time saver and again, I'm guessing that there is an algorithm in the background that assists with the accuracy or improves the accuracy, which would be very important. Right, that's grand. So that's power functions, logs, roots, and so on. Okay, so we leave that there.